It's Coulomb's law. It is very, very easy. I think it is something like a high school difficulty, in my opinion. I suppose all of you have studied it before. So, but actually, I need to talk about it. Okay. So in this chapter, there are three sections. The Coulomb's law, charge is quantized, charge is conserved. Actually, only the first section is that important. So I bold it. Okay. Well, magic. There are two glass rods, were each rod with skew cloth. So this one and this one, glass rod and skew cloth, and one was suspended by thread. So you'll find that they repel each other. There are force pushing this one to that side and pushing this one to another side. So when they are close to each other, they repel each other. Repel, 排斥, 排斥. The plastic wad was wrapped with fur. So this one is changed to plastic, and okay, they will attract each other. But actually, I don't think this is very important. But so this page only tells you that okay, for the same material, they may try to repel each other if you just use a cloth to wrap them. And for this one, if you change one of it to a plastic rod, they will attract each other. So that's the difference between them. Glass rod is corresponding to the cell close and the plastic is... I don't think so. Okay. that's why I say it's not really important. It's just introductory. So actually, during the exam, mainly about the calculation. Although I hope it won't be too difficult for you. So for this page, two charge rods of the same size repel each other. So it tries to explain why they have some difference. For the upper one, it mentioned that they have positive charge on the two rods, so that they will repel. And for the lower one, this one has positive charge, this one has negative charge, so that they will attract each other. So this is what you learn during the primary school, right? Okay, so actually the material are classified based on the ability to move charge. There are totally four here. The first one is a conductor, 导体, 导体. The material in which a significant number of electrons are free to move. 有自由电子了，有自由电子。Example includes metal. Mainly the metals are conductors. But of course there are some exceptions, but it's not important here. And the second type is the insulator. Insulator is non-conductors. So there are not much free electrons, something like the rubber, the plastic, and the glass. And the semiconductor has a conductivity lies between the conductor and the insulators, the semiconductors. When you learn the chemistry in the periodic table, is in the middle, something like the silicon germanium for the computer chip. So actually, in my lab, we mainly work on the semiconductor chip. And this one is a superconductor. Superconductor is some very fancy stuff. A material that have perfect conductors. They are perfect conductors, allowing charge to move without any hindrance. 没有任何阻力的。So a few weeks ago, I met a high school classmate. He worked on the quantum computer stuff. So he told me that for the superconductors, he needs some chambers so that within it is something like hundreds of millikelvin. 就是1K 度以下的几百 milK 的温度。So it needs something like the liquid helium to make the temperature very low, so that some sort of material can be like the superconductors. Okay, for this one, well, very long, lots of text. So for charged particles, you have, well, actually, when you learn this stuff in high school during the chemistry class, you're supposed to know that within an atom there are some protons, neutrons, and electrons. So the protons have positive charge. The neutron is neutral, electrically neutral. That means no charge. And for the electrons, there are negative charge, so that they have the same number of protons and electrons. So that within an atom, it is electrically neutral. But maybe there are some iron, something like that. This is the chemistry class. And actually, positive ion, okay, this is what I mentioned. And for the conduction electron, there are actually some free electrons. For the metal, something like the nuclear is stuck in a fixed shape. And actually, the electrons are free to move in some sort. Maybe it can move to here or there. But actually, it cannot go outside. But actually, they are some sort of free to move within the conductor. Okay. So for this case, it mentioned that the conduction electron in the copper rod are repelled to the far end of the rod by the negative charge on the plastic rod. So it tried to explain why they are attracting each other. So it mentioned that for this one, for the plastic, it has some negative charge here. So for this conductor, the electron try to move to this part. So this part will be positive charge, and this part will be negative charge. Then they will attract each other. Actually, the overall copper is still electrically neutral, but the charge go to this part rather than staying here. So that it try to explain why these two rods will attract each other. Do you consider? Do you think why the electron will will go here, not stay here, so that they repel each other. Anybody knows? You can raise your hand so that you can have bonus.
Because the electrons in the cooker, it has the same sign with the plastic rod, and so it will move to another side because they repel each other because they have same charge.
你要不要说中文？那为什么它不全部都挤在这边，那边是正的？
因为就是跟它互相就是同号的电荷是相斥的，所以就会跑出来。因为正电荷是不能移动的，因为在那个原子核里嘛，但是只有电子是自由移动的，所以它就会往反方向。
Yeah, you get the keyword. So, how to do? Oh, 给我了吗？ Okay. Okay, actually, the idea is that the positive charge are the nuclear, so that they cannot move freely. So actually, for the electron, they are free to move, so that they are repelled by this plastic rod, and then it tries to go here and leave this part positively charged. So for the charge, I suppose you have learned the current in the circuit analysis. So it's just like the derivative of the charge with respect to the time is the current. So the SI unit for the Coulomb, the SI unit of the charge is the Coulomb, C, which is A over AS, A times S. So for physics, the unit is very important. Make sure you write the correct unit. Yeah. So this is the most important part for this chapter, the Coulomb's law. Okay, the Coulomb's law describes the electrostatic force between the two charged particles. Actually, one charged particle, Q1, and another one is Q2. They have a distance separated by R, so that there is a force acting on both of them. The force is of course a vector, so I write it like this. So with this arrow is a vector. This is also a vector, the R, but this this head, R head. This one means the unit vector, which means the magnitude is 1. Magnitude is 1. Okay. So actually, if you write it in a scalar form, so just move away this arrow and forget this part, like this, like this. Sorry. And remove the arrow. Then this is the scalar form of the Coulomb's law. So actually this is 1 over 4 pi epsilon 0 Q1 times Q2 over R squared. I suppose you have learned this in the high school. And actually the epsilon 0 is the permittivity constant, 8.85 times 10 to minus 12. Times 10 to minus 12. Okay, yeah. And for this one, for this one 1 over 4 pi epsilon 0, we sometimes will write it as k, which is 8.99 times 10 to 9 Newton meter square per Coulomb square, which is usually used because for this one you have this term here. So the beauty of this Coulomb's law is that no matter how which side of the charge Q1 and Q2 is, they are correct. Okay, I need to mention that. Okay, I need to mention that. Okay, for F and the R, the magnitude of R hat is 1, and the direction is that for this charge, it is pointing that way for R. For Q1, pointing the right side. For Q2, pointing the left side. So the R hat for the two particles are different. But no matter whether they are positive or negative, this formula is correct because as Q1 and Q2 are all positive, and this one is positive, so that the F pointing with the same direction of our head. So as Q1 and Q2 are negative, because negative times negative is positive. So F also has the same direction as our head. But if Q1 and one of Q1 is positive, one of Q2 is negative, this one is negative times our head, F will pointing the left side for Q1. So it matches that matches this particle with the same sign of electrical charge repel each other, and particle with opposite signs attract each other. So actually this is very simple. Okay, for this one, huh? 再讲一次。啊。对呀，对呀。所以so I recap in Chinese once. 对于Q1 来说，那个 R hat 是往这个方向的，但是对于 Q2 来说，那个 R 是往反方向的，所以那个意思是说， 所以对于 Q1 它是这个方向 for Q1， 但是对于 Q2 来说，这个 R head 是往反方向的 for Q2。所以你要注意的是 R head 是怎么定义。我对于 Q1 的话，我等于说我站在 Q2， 我看着 Q1， 那我往前的方向就是 R head 的方向。我反过来，我现在看 Q2， 我就站在 Q1 的方向，Q1 的地方我看着 Q2， 那 R head 就是往左的方向。需要 Cantonese 吗？不用吧。Any other questions? No? Okay, go on. So this also mentioned that so if they have the same sign of charge, positive, they repel each other. They have negative, then they also repel each other. If one of them has positive charge, one of them has negative charge, they attract each other. So actually, yeah. So for this case, if there are more than two charges, so you need to consider the vector sum for all the electrostatic force for a specific charges, which means that if there are n charges, then the electrostatic force acting on one will be the electrostatic force between 1 and 2, 1 and 3, and so on to 1 and 1 to n. So you add all the n minus 1 forces together so that it is a total force acting on the charge 1. So this is the multi-electrostatic forces. This is quite troublesome because adding vectors are more troubles. I think you have calculated vector summation before. So for this part, shell theory, there are two shell theories for the electrostatic force. The first one is that charged particle outside a shell with the charge uniformly distributed on the surface is attracted or repelled as if the shell charge were concerned as a particle at the center. 这个是说啊charge particle outside the shell， 就是有一个球壳，然后有电荷均匀的分布在表面的时候啊，它就看起来像一个全部都集中在它的中心一样。A charged particle outside a shell with charge uniformly distributed on the surface. Yeah, uniformly distributed on the surface is a keyword. As if the shell charge were concentrated as a particle at its center is another keyword for this shell theory. It tells you that these two cases are the same. And for theory 2, a charged particle inside a shell with charge uniformly distributed on the surface has no net force acting on it due to the shell. Also uniformly distributed and no net force acting on it inside a shell. Inside a shell. 就是说，一个球壳，它如果电荷都均匀分布在表面的话， 它就不会有任何的静作用力作用在它里面的部分。Actually, this is quite difficult to prove. This is quite difficult to prove. When I study physics in my bachelor study, the TA tells us that actually Newton is not hit by a fallen apple. This story is fake. And actually, what he suffered at that time is that he cannot do the integration for the gravity. Maybe I try to explain it to you. At that time, Newton's suffers from a problem like this. Actually, for example, this is the Earth. And actually, if we are outside the Earth, then we will attract by the Earth, right? And we have something like the G M R square F, right? And actually, if you are inside the Earth and assume the Earth is uniform, actually the outside part will not have any net force to you if you are here. If you are here. And the TA tells us that actually Newton's is suffer from this integration. Assume the Earth is a circle, is a sphere, and so that by symmetry, of course, there are no net force in this direction. But for this direction, actually, it is something like this part should be cancelled with this part. And this integration is very difficult. And I was so naive, and I tried to calculate it at home, but I failed. So yeah. So this is what Newton's facing at that time, not hidden by an apple. Okay, we go back here. So I think this is something similar to that case. Not exactly, but something similar. But actually, these two theory may be some sort of important stuff to memory, because this is really physics. Physics is something try to describing the world. The math is on top of the physics to calculate what you want to calculate, but the physics itself is trying to describing the world. If you actually, this is the first step. If the first step is incorrect, even you have fancy mathematics skill, then you calculate the wrong answer. So the checkpoint tool figure shows two protons. This one is proton, P are protons. One electron here. Oh, I have already showed it here. Pretend you don't see this part. Okay. On the center portion, what is the direction of the force due to the electron? central portion is okay due to the force due to the electron, which is the direction of the force due to the other pole. On the central portion, what is the direction of the force due to the? Okay, actually this is quite simple and stupid. So it tries to ask you for the central proton, what is the direction of the force due to the electron? The force due to the electron. Okay, this is negative, this is positive. So they attract each other. So this is point the left towards the electron. So pointing left for the A. For the B, the force due to other proton. This is positive, this is also positive. So that they repel each other. So that also away from the other proton, which means also pointing to the left. The net force, A is pointing to the left, B is pointing to the left, and add them together, also pointing to the left for the C. So very simple. Any questions? Okay. Okay, maybe let's move on. Because I need to finish the 3 chapters in this week, so that we don't have break today. And if you need to go somewhere, just help yourself. So for this sample problem, figure A shows 2 positive charge Q1, Q2 fixed in the place on an x-axis. This is x-axis. The charge are Q1, Q2, 1.6 times 10 to minus 19, 3.2 times 10 to minus 19. And the particle separation is R equals to 0.02 meter, 2 centimeters between them. What are the magnitude and the direction of the electrostatic force on particle 1 from particle 2? Okay, so it's very simple. So actually F12 is just 1 over 4 pi epsilon, which is K times Q1, Q2 over R square, which is 8.99 times 10 to 9 times 1.6 times 10 to minus 19 times 3.2 times 10 to minus 19 over 0.02 square. Okay, just put all the numbers in the Coulomb's law. And what you need to be careful is the unit. Actually, the unit meter. For some question, it will have centimeters. So make sure you convert to meters, because the original SI unit is meter, not centimeters. And here should be a C, Coulomb. So the answer is 1.15 times 10 to minus 24 Newton. 1.15 times 10 to minus 24 Newton. And actually, the direction is point to the negative x-axis. Direction, negative x-axis. So any questions? No questions. K 对不起 K 本来想写 E over 4 pi epsilon 0，应该是 K 才对。Actually, during the exam, I'll give you the constant. Something like the epsilon 0 is 8.85 times 10 to minus 12. The K 1 over 4 pi epsilon 0 is 8.99 times 10 to 9. But actually, when I prepare the slides, I already memorized it. So for B, figure C is identical to the previous one, except Q3 is here. Q3 is here. Now lies on the x-axis between particle 1 and particle 2. Particle 3 has charge minus 3.2 times 10 to minus 19 and is at a distance 3r over 4. So this is 3r over 4, 1r over 4 here. What is the net electrostatic force on particle 1 due to particle 2 and 3? So for the previous one, you can write it like this, because F is a vector. So this is the magnitude, not including the minus sign, but actually the x-axis is pointing to the right hand side. So if it is pointing to the left hand side, it is minus. This is Newton, and this is the unit vector on the x-axis. We will write it like I for the x-axis, J for the y-axis, and K for the z-axis. Usually for the IJ, we don't write the dot because it is merged with the head. So we in the textbook you will not see something like this, but this one you will only see this part with the head, and also J. Maybe I use the mouse is better looking. So for B, so actually go back to this example. What is the net electrostatic force on the particle 1 due to 2 and 3? Because particle 1 due to 2 we have already calculated in the previous page, so we only need to calculate F13 is similar, which is K Q1 Q3 over the distance is 3 over 4 r square. So it is actually 8.99 times 10 to 9 times 1.6 times 3.2 minus times 10 to minus 19 square over 9 over 16. R square is 0.02 square. Okay. So maybe we can only calculate the magnitude like this. So this is positive. So the magnitude of F13 is 2.05 times 10 to minus 24 Newton. And so F1 net is F12 plus F13. So for F12 is point to left side and F13 is point to this side because this is positive. This is Q1 is positive, Q3 is negative, so they attract each other. So F13 point to the right hand side. So it is something like minus 1.15 plus 2.05 times 10 to minus 24, which is 9 times 10 to minus 25 Newton. And actually, if you want to write it as a vector, this is I. And this is for this one. Any questions? Any questions? It should be quite simple, right? Okay, I go on. So for this one, Q3 is removed or it moved to here. It moved to here with a 60-degree angle with Q1 and Q2. So what is the net electrostatic force on particle 1 due to particle 2 and 4? Actually, okay, it has charge. Well, so I think this one should be Q4 rather than Q2. But actually, the value are the same. So for F14, the magnitude is actually the same as S13, which is 2.5 times 10 to minus 24 Newton. And yeah, this is 2.05. Ouch. 2.05 times 10 to minus 24 Newton. So you know the troublesome for the vector summing, you need to separate into two parts. The x-axis is F14, maybe I don't make it a vector. So this is actually F14 cosine theta. And this one is F14 sine theta. F14 sine theta. So actually F14 is just this one is let me see, 2.05 times 10 to minus 24 cosine 60 degree is just 1.025 times 10 to minus 24. Newton I plus 1.78 times 10 to minus 24 Newton J. So all are positive. So F1 net, we just add F1 net. We just add them together. So it would become minus 1.25 times 10 to minus 25 Newton I plus 1.78 times 10 to minus 24 Newton J head. Any questions? Okay, no questions. Okay, so for the next example, okay, figure A shows two particles. Figure A shows two particles fixed in space. They are fixed. Q1 is plus 8Q at the origin, and particle of charge Q2 minus 2Q at x equals L. So they are separated by L, capital L. At what point other than infinity or far away can proton be placed so that it is in equilibrium? At what point other than infinite, okay, that is in equilibrium, the net force on it is 0. Is that equilibrium stable or unstable? Oh, this is a very tricky question. So which means that we have two charges here, Q1 and Q2. If you want to place a charge, a positive charge somewhere, but not infinitely far away. So for this charge, you may be either attracted or repelled by Q1 and Q2. But the force will be cancelled. So it tries to ask you where you can put it so that it is in an equilibrium point, and try to ask you whether the equilibrium point is stable or unstable. But that is another question. Let me finish this part first. So for figure B, if the positive charge is placed between Q1 and Q2, so this charge will be repelled by Q1, so that the force will point to the right side, right? So for the F1. And for Q2, they are attracting each other. So this force acting on P is also pointing to the right hand side. So these two forces are pointing to the right hand side also. So they have no way to cancel each other. So this one is impossible. So this is impossible. And for this one, okay, so there are two more cases. One is on the left side, one is on the right side. Actually, this one is also impossible because now you need to consider the amount of charge. Q1 is 8Q, Q2 is minus 2Q. So actually, this force, the force acting on S by Q1 must be larger than the force acting on S from Q2, which means F1 must be larger than F2 because it is also closer to it, and also this is also stronger. This is the amount of charge here is also larger. So F1 must be larger than F2, right? So for this case, it is also impossible to place the particle on the left side. This is also impossible. So for the final case, this is the only possible way because this one is larger, this one is smaller. But for the distance, this one is larger. This is I can write it R1, R2 is smaller. So the force is something like this: Q1, Q2, R squared. So for Q1 is larger. Maybe it's just Q. You can Q1, R1. So this one is larger, this one is smaller, so that they have exactly one situation that F1 and F2 can cancel each other. So the only possible situation is D. So actually, we need to calculate where it is. Okay. So for this case, so this is L. This is L. and we assume this is x, this is x. So for F1 is k times 8q, and this charge, it does not tell you how large it is, but actually we call it QP, but as it is not important. And the distance is x squared. So for F1. And for F2, also K, this is 2Q. And also QP over x minus L squared. Because for this is x, this is out. So this must be x minus L for this. So K can be cancelled, QP can be cancelled, Q can be cancelled. Two, so this is 4. So we expand them. Okay, this is 4x squared minus, so here it has a 4 here, 8xl plus 4l squared equals x squared. So actually 3x squared minus xxl plus 4l squared. Anyone don't know how to solve this? 1元2次方程啊，有没有人不会解的？ So actually, there are 2 solutions for this. One is 2 over 3L, and another one is 2L. Actually, the first one is rejected because if x is equal to 2/3 of L, the P would be lie here. So this is not what we expect. We expect the charge should be on the right hand side of Q2. So this is reject. So the only answer is 2L. Only answer is 2L. So for this L, it should be placed somewhere here. This one is not correct. And it tried to ask you whether it is stable or unstable. Actually, it is unstable. I'm not sure you can accept this, but actually in the textbook it tells you that the reason is not very good for me, I think. it says, I forgot what it says. But actually, when I read it, I don't feel very comfortable for its explanation. So I try to tell you why I say it's unstable. Actually, the Fnet is something like K 8 QP over x squared minus K 2Q QP x minus L. L squared. Actually, it is just move that to this side. Move it to that side. Oh, shit. QP over x squared minus K 2QP x minus L squared. So factor or the common factor out. Okay. So it would become 4 over x squared minus x 1 over x minus L squared. Something like this. Actually, I don't switch back because it will disappear. Actually, to ask you whether it is stable or unstable means, if you try to move a little bit off that position, then it will go away. It is something like actually it is something like when you have a curve like this, and then you throw a ball somewhere, and then you will try to go until it stops here. Then we will say this is stable. Because it's maybe some wind or you just put it to here, it will try to go back to this position. But sometimes it will something look like this. If you just put it very perfectly here, it will not move. But if some wind just blow from this side and then it will just go away. This is what we call unstable. I'm not sure whether you can watch at the back of the classroom, but it's just some simple demonstration of whether it's stable or unstable. So. People usually like the unstable stuff. Something like we want to have maybe a stick, and then we try to hold it like this. This is something like an unstable system. We try to stabilize it. So we move on. So here, what we really do is that if we change x to x plus delta x, or sorry, it should be 2L 2L plus delta x, because what we calculate x is 2L, right? X is 2L. So if x is changed from 2L to 2L plus delta x, which means it moves forward a little bit, then just consider this one. This one does not relate to whether it is larger or it is just a factor, right? Because at x is equal to 2L, f net is 0, right? So what we care is that if x becomes 2L plus delta x, just like this is 2L. If I just move a little bit forward, if there is a force pushing me backward, then it will be some kind of stable. If I move this way a little bit, then if there is some force pushing me backward, then this point is what we call the stable equilibrium point. If I just move a little bit forward and then the force increase and then I just go away, then it's unstable. You get this idea. So for here, this part is something like 2L plus delta x minus 1 over 2L minus L square. So it is like 4L square plus 4L delta x. Here should be plus delta x. So this is delta x square minus L plus delta x square, L square plus 2L delta x plus delta x square. Okay. So it will become 1 L square plus L delta x plus 4 delta x square minus this one. We need to consider whether the first term is larger or the second term is larger. Actually, the first term is larger because when we consider the delta x, which should be much less than L. So usually for the x squared term, we will ignore it. And for here, it is L delta x. This is 2L delta x. So this one is larger, but it is in the denominator, so that this one should be larger, this one should be smaller. And it turns out that when you subtract this term by this term, it is larger than 0. So, which means that when the charge moves from 2L to 2L plus delta x, the force becomes positive, which means that if it is at 2L and it's moved to 2L plus delta x, the force is positive, and then the force will push it away. And similarly, if you just move it to minus delta x, all the derivation is similar, except this one is negative, this one is negative, so that this one is negative also. So if it moves from 2L to 2L minus delta x, the force will be negative, and it goes to the negative direction. So this is the unstable equilibrium point. Okay. So the rest of the stuff is not so important, but I need to finish it. Yeah, the charge is quantized. Electrical charge is quantized. Yeah. Okay. As you know, yeah, we have electron, but an electron cannot even separate into smaller particles, so that the unit charge is what we call E, the elementary charge, which is 1.6 times 10 to minus 19 Coulomb. You cannot make it something like 0.8 times 10 to minus 19 E. Half E is not does not exist. So whenever you have a charge, it must be an integer multiplied by the elementary charge, and must be either positive or negative integer, or maybe zero is also possible. Zero is also possible if it is electrically neutral. But n must be plus or minus 1, 2, 3, 4, 5, and so on. And here, the charge of three particles, electron, 电子, proton, 质子, neutron, 中子, okay. So when a physics quantity such as a charge can have only discrete value rather than any value, we say that the quantity is quantized. It is possible for the example to find the particle has no charge, or yeah, it can be 10e minus 6e. Positive or negative are possible, but 3.57e is not possible. Initially, a sphere has a charge of minus 50e, and sphere B has charge of 20e. The spheres are made of conducting material and are identical in size. If the spheres are then touched, what is the resulting charge on sphere A?哦，是，你那么厉害，可不可以沉默一下？让其他同学都想一想。Okay. Actually, when sphere A and sphere B touch each other, yeah, minus 15e and plus 20e, it will cancel part of them, so that the total charge will be minus 30, and then separate to sphere A and sphere 2 equally, as they are identical in size. So for sphere A, it has minus 15e, and for sphere B, it has minus 15e also. Okay, let's move on. The nucleus in an iron atom has a radius about 4 times 10 to minus 15 meter and contain 26 proton. 一个铁的原子啊，半径是这个，然后有26个质子。What is the magnitude of the repulsive electrostatic force between two protons that are separated by? Okay, we just go through it quickly because it is pretty simple, I think. So F is K times E squared divided by 4 times 10 to minus 15 square. Sorry, it should be R square. So this is 8.99 times 10 to minus 9 times 1.6 times 10 to minus 19 over 4 times 10 to minus 15 square. So the force is 14 Newton. 好像蛮奇怪的，看一下。Oh, it only mentioned 2 photons, so actually should be positive E. Oh, that's correct. Oh, this should be a square here. This should be a square here. So 14 Newton. Okay, this is not very important, but just plug in the value in the formula. And actually, for part B, what is the magnitude of the gravitational force between those same 2 photons? Actually, when you learn mechanics in V1, you should know F equals Gm m. Actually, you don't need to care about this, but I just want to tell you this only. So in between, this is not important, so I just write the answer. So the gravitational force between the 2 photons is just 1.2 times 10 to minus 35 Newton. And the force repelling 2 photons is 14 Newton. Because there are 2 positive charges, they are very close to each other. And the gravitational force, which you learn in the mechanics, is just something times 10 to minus 35 Newton. So actually, the nuclear model, the atom model, which you learn in the chemistry in high school, is not complete. Cannot really explain why the proton can be like that. There are many positive charge very close to each other in the nuclear. So actually, if you are interested in it, you can read about chapter 44. It's about the quark. So this is about the standard model of elementary particles. This is actually what the physicians do. They try to separate the proton, the neutron, the electron. Electron cannot be separated. They try to further separate the proton and neutron into smaller elementary particles, like the quark. Let me see whether I can. Actually, you don't really need to know, but I just let you know. The standard model of the elementary particle. So it has up, down, chime, strange, top, bottom, which are quarks. There are some leptons and boson, and this is what we call the Higgs boson, the Higgs boson, which is very famous. A few years ago, what we call the 上帝粒子啊，上帝粒子，什么希格斯玻色子，Actually, they try to separate the particle into smaller parts so that they try to model some kinds of charge, mass, and spin for the further elementary particles. But actually, I'm not a physician. I don't really know about that. I only learn some very basic concept about that. But just let you know, what you have learned or what you will learn will never be really correct. They may become wrong sometimes later, or maybe now. So this is about the charges conserved. Oh, maybe just a little bit OT, but I'll finish soon. The charge is conserved. The charge cannot be created or eliminated, but there are some electron and collide with the anti-electron so that it can become some gamma ray, and gamma ray can become electron and anti-electron, but this is not very important as I mentioned before. So what is actually the gamma? Gamma you can see in the electromagnetic spectrum. Or when you use Wi-Fi, it is something like 10 to 9 hertz, which is gigahertz. And actually, the higher the frequency, the higher the energy it is. So come to here, it is the gamma wave. And additional example, I don't think it is really important. So maybe we just stop here.